Task graphs. A task graph is a graph, oriented graph with which vertex are tasks and edges represent the dependencies between them. An important kind is data flow graphs, DFGs. In this case, the edges represent the transmission of token of data between tasks. And there are no other exchanges of data between the task outside the one represented by the edge. That's the important property. So for instance, two tasks cannot share some data using some global variable in this model. Usually a task graph is acyclic. We call that a DAG, directed acyclic graph. And when it's a DAG, there is at least one execution sequence that respects all the dependencies. If there is loop in the task graph, this is not true. Let's take two examples. In here, I have a first example. This first example, the tasks are mostly the same, very similar, and I have a tree of reduction to compute the minimum of a set of values in parallel. A different kind of task graph. In this case, each task performs a different function. Okay, and in this case, this is a set of functions that have to be performed to display some polygons on the screen. And in this case, we have a pipeline organization of the task. To enter the data dependencies in the task graph, you can have two techniques. The first one, static and dynamic. Static, you know at compile time. In this case, you can use a static scheduling. If the dependencies between the tasks are not known before runtime, you need some dynamic scheduling technique, because in this case, you will discover at runtime when a task can be launched because its data are ready. And in this case, particular case, you will need to track the data dependencies at runtime. And usually you need some library, a runtime library to perform that. What is difficult here is to make that efficient, because tracking all the memory blocks can be very costly. So you have to restrict yourself to some structure or simplification of the tracking to make it efficient. So just to give you an example how that is being used in practice, here I'm considering the OpenMPSS programming APIs that is developed by the Barcelona Supercomputing Center. And in this case, I have two tasks, okay, two kind of tasks, because that will be created at runtime. So in here, I will create two n-1 task. And the issue I have here is that the compiler or the runtime will have a lot of difficulties to find what is in and out, because that would require to look at what happens in propagate and in the correct functions. So what is done here to help the runtime to track the dependencies, it's to add some pragmas. This is the two pragmas, and it specifies what is the data that will be in, that is read by the by the task, and written by the task, and read and written by the task. So the compiler will be able to generate the runtime calls that will allow the runtime to track the data dependencies between the task, and then the scheduler will know when it is possible to launch an instance of the correct function or of the propagate function, depending on the data dependencies. Look at what is being done with the StarPU runtime system. This is a very well-known system used in many libraries, and so it's a good example to see what you can expect from some runtime task management. The pointers to the runtime systems and APIs. So see you in class.